We're talking about particle in a box. We described our system. Okay. And we set up bounds for our system. Can you guys tell me anything about this quantum system, or this model system we're looking at? Has 3 regions. Okay. And how many dimensions is the particle traveling in? 1. Okay. Where are we permitting the particle to travel? Oh, I used yellow for the regions, right? Got region 1, region 2, region 3. Okay. What's special about these regions? Yep. What's the potential of region 1? Yep. Region 2? Yep. Region 3? Yep. Infinite. Okay. Where is our particle contained? Yep. In 2 from 0 to A. Oops, we did lower. We did A, right? Not L. Okay. A. And we had some walls. And what did we say specifically about the walls? They're impenetrable. That might seem goofy. We'll see in the future why you have to specify that. Okay? All right. We talked about the value of X in these regions, right? So region, region number, and X value in region 1, 2, and 3. What was the value that X would have in region 1? Yep, less than or equal to 0. What about region 2? Yep. And it can take on the value of 0. Ooh, that's terrible. 0 or A, right? And then what about region 3? Yep, greater than or equal to A. Okay. Now, what we have to try and do is apply the Schrodinger equation to each of these regions and satisfy the bounds of each region. Once we do that, we'll have to think about different wave functions, what mathematical functions will work for our setup and which ones won't. After we do that, we have to normalize our wave function. Make sure we get a value, if we look at this whole thing, of 1, and then we'll start applying. Does that make sense? Or at least are you following the pattern right now, or workflow? Okay. The spot that we focus in on are the potentials. The benefit to this is what do you know about regions 1 and 2 and their potentials? They're both what? They're both infinite. So really we can look at them and chances are the math is going to be the same. So I don't know who moves this. Does Dr. Ogawa move it? See, I always move it over here so I don't poke it, but somebody moves it where it's like, is Dr. Yule as tall as me? Dr. Kluznik seems like a giant to me. I don't know, I'm short. All right, anyways. V is equal to an infinite in which regions? Yeah, 1. And what'd you say? 3? I thought you said 4 for a second. Like, we don't have a region 4. Okay, we need to apply the Schrodinger equation. What's the generic Schrodinger equation? Yep. Yep. Hamiltonian psi, E psi. Okay. Now, let's look at the generic Hamiltonian operator when we break this. What 2 types of energy are we going to break it into? Yep, kinetic. Okay, tell me the kinetic energy portion. 2m, yep. Yeah, of whatever we're considering. And what, I already gave it away, but what dimension are we looking at? Yeah, x. I care more about this part. If you screw up this part, whatever. Okay, so that's the kinetic energy portion. What about the potential energy? How are we going to describe that? Yeah, it's V, which is a function of x. So we assume that. And then we got to multiply this by our wave function, and that gets us to E psi, right? Okay, let's apply region 1 and 3 potential. And what's the potential equal to for regions 1 and 3 again? Okay. So now let's plug that into our equation. We get negative h bar squared 2m second derivative of x plus, what's this term, the potential term now? Infinity, yeah. Times psi is equal to E psi. Okay. We have an infinite potential. If this exists, what does that imply about the energy? Yeah. This implies that E is equal to infinity. Can that happen? No, why not? Why can't we have a system with infinite energy? What's stopping us? Exactly. The first law of thermodynamics says that can't fucking happen. Get out of here. This doesn't happen. Okay. So we know we can't have an infinite energy. We know that our potential has to be infinity. This thing has to hang around. What is our only other option to make this a realistic system? Something about the wave function. What is the value of the wave function? Yeah. So this implies that that is infinite. That's impossible. You spent a whole semester talking about thermo and showing the first law can't be broken. That's impossible. So our only option is, just like you said, Ellen, therefore psi must equal 0. Awesome. So what does that say about regions 1 and 3? Do we have to worry about constructing a wave function or figuring out what works there? No, because its value is 0. Great. Don't have to worry about that. What region do we have to worry about now, though? We gotta think about 2. We're going to apply the Schrodinger equation to region 2. The other thing we have to keep in mind is at these walls, remember, region 1 includes 0 and region 3 includes A. What does the value of the wave function have to be at these edges? 0. Because we have said it's 0 in regions 1 and 3. So we're going to have to keep those things in mind. We'll have to think about what functions will work and what won't work and what satisfies our Schrodinger equation. Okay? Am I okay to erase that side? Okay. Let's pop back to region 2. What's the value of the potential in region 2? Yep. Okay. Let's start with a generic Schrodinger equation. What's the generic Schrodinger equation? Or the time-independent one? Yep. Yep. Hamiltonian psi is equal to E psi. Okay. Now let's break this apart into kinetic and potential energy terms. Kinetic part, negative. Yep. Yep. Yeah, your second derivatives. It's okay. I thought you said it all the way. I'm like deaf in this here. And then what else do we have to tack on? Yeah. Yep, we say the potential is some function of x. What else? Yeah. And then the other side of the equation? Yeah, E psi. Okay. Can we simplify this in any way with what we know? Seeing head nods, what can we get rid of? Yeah. The reason it's 0, we set it to 0. So now, how does our equation change? We get negative h bar squared 2m. What do we take in the second derivative of? Yeah, the wave function. And that's equal to what? Yeah. Okay. Which portion of this equation is the most complicated? Yeah, this second derivative. This is just a function times a scalar. This is just a collection of constants. This is the part that we have to worry about. So we got to think about what type of functions could work or couldn't work. The other thing is in your differential equations class, if you had an unknown function, what did you do to try and find that unknown function? Which may have been a while for people. Or you may not know in general because it's like, what's going on in that class? Yeah. Sometimes you move things around and set one side equal to 0 because it's easy to find those points. I'm going to say asymptotes, but it's probably wrong. Some person will be mad. The people next to us will be mad that I said that. You want to look for things that are 0. But this is a simple differential equation for what we have. When we get to more complex systems, we can't really just think about stuff. We'll have to solve for things. Here, it's nice because we can think about it. Okay, so question. I'm going to erase this thing. which I'll probably need to draw back up there again. What functions would this work for? That's basically what we're going to ask. Question. We know need take a second derivative. Our function and get a constant. Plus that's, or well, and the same function. What mathematical function could we use? So basically what we're saying is when we take a second derivative, where do we, of some function that depends on x, where do we get that same function out times a constant? Think back to your calculus classes. What functions do you know of that could do this? Yep, e to the plus minus I k x. I love those functions. Sine. And then we'd need some, sine x wouldn't work. Well, it sort of works. What would the constant of sine x be? 1. So if we want to get a constant out front, what would we put in here? Yeah, kx. Okay, sine's right. Any other ones that come to your head? Yep, cosine also works. And again, we need a kx. So these are some possible functions that sine could, or excuse me, that psi could be. Now, what is our job next is to look at the bounds, look at the areas, the constrictions we have for our wave functions, and see which of these would work and which of them wouldn't work. In reality, did you guys talk about Fourier transforms and instrumental at all? Did you talk about them in any of your math classes? Okay. What do you know about Fourier transforms from instrumental? Or do you just remember the word Fourier transform? Mm-hmm. Yeah, you get out usable spectra from using fancy mathematics. Did they explain what the mathematics really is? Okay, basically you can turn any function into a combination of sines and cosines. Any function can be described that way for the most part, if you have enough points. What do you know about the relationship between these two things and e's to the whatever? Or have you ever talked about, I think it's Euler's relationship? Maybe not. This is actually made up of a combination of these two guys and vice versa. They're really the same thing. You might be going, what the hell? No way. Yeah, plot them sometime, and you'll see they're the same. Okay. Let's now look at our bounds, and let's see, can we rule any of these guys out? What's going to work, what won't? Okay. So from bounds, And what I mean by bounds are where our regions touch. So psi at 0, where we hit the first edge of that barrier, what does the value of that wave function have to be from what we established earlier? Has to be 0. Okay, let's plug in 0 for some of these things and let's see what we get. Sine of k is 0. What's that going to be? Yep. Sine of 0, which is just 0. Cosine of k is 0. What's that going to work out to be? Yeah. What does that tell us? It's not cosine. Can't be cosine. So this guy's gone. And we're left over with these two. What about IKX? Yeah, if you plug in a 0 here, it actually could work if you have a combination of those two. We could pick e to the IKX, but Euler's theorem basically states you already have sines and cosines in there. You have e to the IKX, that's also equal to cosine x plus I sine theta. Which one do you think would be easier to deal with? Schneider's pretty happy down there, I guess. Yeah, I'd go with just sine. It's easier. You can derive the whole particle in a box through this way. I'm not going to make you do that. Let's just hang with sine. Okay. So this one, we could look at it. We're basically looking at the same thing, though, if we look at sine. So let's just exclude this one for now. Okay, we've looked at our first bound. What do we have to do next? Yeah. We got to consider our other bound. At our other bound. And Ellen, you said at what point? Yep. What does that have to equal? Yep. Okay. So let's come up with a generic wave function. We know it has to be a function of what mathematical function? It has to be sine. So let's do sine kx. And wave functions, to be valid, what do they have to be over a certain region? Starts with an n. Got to be normalized. So how have we always factored for normalizations? At least. Yeah. Yeah, set it equal to 1, do a probability thing. What do we tack on the front of our function? Yeah, n, a constant. We're going to go a little different, a little wild. We're going to go with a as our normalization constant. I know, terrible. Okay. Let's get to just this sine part, though. We're going to move a over, divide by that. get this. Oh, except what is our x value equal to? Yep. A. Where is sine 0? It's any whole number.
With pi.
Yes. So nice thing about sine, it's a periodic function. At any whole number factor of pi, it's 0, right? So what does k times a, what does that have to be equal to? We want this to be 0, or well, excuse me, we want this to be what? You said pi in here, right, Lily? But it had to be a whole number. So we got pi. What are we going to multiply it by? Or what restriction would you make? World's your oyster. You can do whatever you want right now. So what would go here?
1 over a.
We're gonna, that's what we're gonna get to soon. How does quantum mechanics differ from classical mechanics? Or classical physics? The word quantum means quantized, right? What does quantized mean? Whole numbers, discrete values. What has to go here? What type of number? Quantized numbers, and you said it earlier too. What numbers got to go here? Or could you give me examples that would work here? 0 would work. What else? 1. What else? 2. Not 1.5 though, right? That screws it up completely. So what number has to go here? Integers. Is a whole number an integer? I can't remember the classification now. I think it is. So some whole number integer. I feel like if I say that, then we get it all. So let's just put something here, a constant here, but we're making a restriction that it has to be a whole number. Let's go with n. So what could n be equal to again? Yep. And it could keep going, right? Okay. Principal quantum number. Quantization showing up again. Okay, but the whole point of this is to try and figure out a value of k that would work for the system. What's k going to be equal to? Yeah. So Lily, like you said, if k has divided by a, when we multiply it through, the a's go away. We're just left over with some factor of pi. Therefore, if we consider our wave function at any point x, what's the formula for our wave function going to look like? A times, Yep. What's our k equal to again? Yep. A, and this is at any point x. I'm going to actually just put it up top here. I like the way it looks. Okay. We have a wave function. It follows our bounds. It should be pretty good, but we have to do one more thing. What do we got to do? We got to normalize it. One more quick question. We tend to leave out 0 a lot of times from this because it's like the quantum particle doesn't exist. So we tend to leave that guy alone. But it could be there. Okay, so what we got to do next? We need to normalize. Okay, tell me the generic formula for normalization. Yep. Yep. D what? Tau. Yep. And what are my bounds? Whatever I tell you, yeah. But for a generic system, A and B, even more generic. Negative infinity. Positive infinity. Okay. Because certain regions of the wave function will be 0 over. Okay, well, let's get specific now. For our system, what's the lower limit? What's the upper limit? 0 to A. Okay, and then we just got to plug in these things. The complex conjugate of this, does it change? No. Why doesn't it change? Yep, no Y's. So we don't have to really worry about it. I x over A and pi x over A. And then what variable are we going to change that d tau to? Yep. Okay, can you simplify that for me? Is there anything you'd pull out or combine? Yep, get rid of a squared, pull that out front. Integral from 0 to A. What about the other stuff? Yep, sine squared n pi x over A dx. Anybody know how to do that integral? From the table? Okay, if you memorize the table, yeah, I don't remember it. Let's pull from table of integrals. That's definitely what it will be. I just want to write the thing that we have. X over 2 minus, 1 over 4a sine 2ax. Okay. Let's do it for our system. Tell me what the integral will be after it gets evaluated, but we don't plug in the bounds. Yep, x over 2. What's our a in this case? Yeah. Okay. Yep. Times sine of what? Yep. And we're going from 0 to what? Okay. Let's start plugging in stuff. First term. Sorry, gotta give you time to scramble things down. Yep, a over 2. Minus a over 4n pi sine. What's gonna happen in here? The a's are gonna cancel, so what are we just left over with? 2n pi, yep. Minus 0 plus a over 4n pi sine of what? Yep. Okay. Can we simplify anything? Sine of 0, what's it always? Yeah. Gone. Any other spots? So that you're saying this one will be 0, right? Why? Yeah, we said n has to be 1, 2, 3. It has to be a whole number. It's a factor of pi. What will this term right here always be? It'll always be 0. That goes away. So I'm going to erase stuff over here. We got 1 is equal to a squared times what? Yep, a over 2. Okay, what was the whole point of what we were doing here? Yeah, find a. Let's manipulate this around. How are you going to do that? Yep, move the fraction over, so we get 2 over a is equal to a squared. What now? Yep. Therefore, our normalized wave function, what would it be? Yep. Times sine of what? Yep, n pi x over a. This is our normalized 1D particle in a box wave function. A lot of times what you'll see is a little n here to indicate what energy level we're talking about. Okay. Next time, what we're going to do is we're going to apply this with a Schrodinger equation and come up with a generic formula for the energy, just like you used with your last daily problem. Then we're going to look at how does changing that n value, what does that really mean? How does that impact something chemical that we can see? Or observe, not see. Any questions about that? Again, try to understand this process. Go through without your notes to see if you can do it. If you can do this, I feel very confident you can do anything else we're going to see coming up. Okay? After we deal with 1D systems, we're going to go to 2D. Then we're going to go to 3D. Then we'll start considering systems that have more complicated potentials. But out of this, we're going to get, like, why does an s orbital look like the way it does? Why does a p orbital look the way it does? Haven't you ever wondered where those goofy ass shapes come from? Like, how did that get figured out? It starts here. All right, no other questions? All right, have a good day.